Hi, welcome to this next episode on the recipe for carefree dependency management in Java projects. Today we look at the fourth item on the recipe, which is performing conflict management in a dedicated file. Let's first take a look where this fits into the topics we have looked at so far. All the items in the recipe so far, including this one, are really about separating concerns. The first item is about defining dependencies between your modules and third-party modules. The different options you have to define such dependencies, but also stressed that it is important to keep this clean from other aspects you may need to define in your setup. One of these aspects are the versions of third-party modules, which you should define in a dedicated file to use the same versions across all your modules and dependency definitions. Then, when you use Gradle or Maven as a dependency management tooling, you should make sure that all other configuration is kept separate from the dependency definitions, which is the third item in the recipe. If we now remember the introductory video for the series, there are basically two major aspects we want the dependency management tools Gradle or Maven to cover for us. The first is obtaining the modules we require, which means downloading third-party modules from a repository, and building, which means compiling and packaging our own modules when required. We saw in the introduction that in certain cases for third-party modules, we also want the dependency management tool to select a version or a variant for us. In the example, we have the case where we need to make a decision between two different versions of Commons.io. And we had the situation where we could use different implementations of the logging framework we use, SLF4j. In the example, we had SLF4j Simple or SLF4j JDK 1.4 as logger implementations. The third example was that we use jar files that contain operating system specific code. In our example, these are the LWJGL native jars. In all of these cases, we can make a choice which concrete implementation of a module, so which jar we would like to use. Sometimes only a certain choice makes sense. For example, if we want to run our application on Windows, we need to select the Windows native jar. In other cases, we can make a choice, like which logger implementation we would like to use. The dependency management tools should help us with this, especially when the choice is clear. To do this, these tools need sufficient information about the different versions or variants of the modules. This information is provided through metadata. We saw that if we look into a repository like Maven Central next to the modules, so next to the jar files, there are additional files containing metadata. There is a POM.XML file, but also there can be an additional module.json file which can contain additional metadata that Gradle supports. The module metadata format was introduced by Gradle because the POM format does not support to express certain information. But because that format is not supported by any other tool than Gradle, many libraries do not take advantage of it yet. And therefore, often metadata is incomplete. For example, in the case of LWJGL, there is no information about which jar belongs to which operating system in the metadata. You can guess it from the name of the jar, but a tool can hardly make an automatic decision only based on the information in the metadata. In other cases, a library may provide a good amount of metadata, but could still contain errors or information that is not quite correct in your context. Therefore, the build tools or dependency management tools provide features that allow you to compensate for missing, incomplete, or wrong metadata. Now, as with the other topics, such patching of information can be done directly in build Gradle or POM.XML files. But the tools provide sufficient features to also separate this out into a separate file. The way I look at it is, if the metadata would be complete and perfect for my setup, for my use of the third-party modules, then no additional information would be needed. The build tools could get all the information they need to decide which versions and variants of modules to use from the metadata. In such a perfect world, I would not have to care about adding any kind of additional information apart from defining my dependencies and selecting versions of third-party modules. And thus, I can keep focusing on declaring the dependencies in the files I use for dependency definition. Now, as I seldomly have this perfect situation, I can look at the dependency rules as a kind of adapter layer that enriches the metadata I have for third-party components in a way that it is rich enough for the tool to solve any version or variant selection conflict. And also, if I discover things that are generally wrong or missing in the metadata of a certain module, I can report this back to the maintainer of this most likely open source module, and thus improve the situation for everyone in the Java ecosystem. By improving metadata of existing modules, the dependency rule files in many Java projects will become easier to maintain over time. Now, how does such a file look concretely? Let's first look at our Gradle setup. The dependency rules file is located in our plugins build next to the configuration of other build concerns. The worst case we can look at is the selection of a logger implementation. With the metadata available for the SLF4J implementations, Gradle won't detect a conflict when selecting two implementations on the class path or module path, because technically both implementations could be loaded together. It's only that the logging framework itself doesn't support that and thus gives a warning when the situation occurs. Ideally, Gradle would detect this conflict of having two implementations up front. This is supported in Gradle's dependency management by the concept of capabilities. For diving deeper into this, I have a video dedicated only to this topic. In short, if two libraries share the same capability, they are mutually exclusive. So you can express that they are both implementations of the same interface and that the build tool should choose one of them. As this information is not yet published in the metadata of the SLF4J modules, we can add it through a rules file. In this case, we don't need to add all the rules manually, but we can just use the Gradle X JVM dependency conflict resolution plugin. This plugin already adds a bunch of rules to enrich the metadata of well-known libraries from Maven Central, and in particular adds a lot of metadata for the various logging frameworks that are out there in the Java ecosystem. Now, with the plugin applied, Gradle detects a conflict. And because in this case there is no globally right solution, we need to make a choice ourselves. With the conflict resolution plugin applied, we can make a choice by using the select statement, where we state that for a certain capability, in this case SLF4J impl, we would like to select a certain implementation if a conflict occurs. In this case, the selection is SLF4J simple. The next topic was the selection of a native jar, a jar that contains code specific to a certain operating system or architecture. As mentioned, in the case of LWJGL, which we use in the example, this information is not yet provided through the metadata. We can use the patch DSL of the conflict resolution plugin to add this information. For example, we state that the jar with the Windows classifier in its name maps to the Windows operating system and the x86 architecture. And we do the same for the other jar files that are available. The underlying Gradle concept we use here is called component metadata rules, so rules that modify or enhance the metadata of existing modules. Information about jars is either added via capabilities or via attributes, which help Gradle to make a certain selection. For more background about attributes in Gradle's dependency management, see my Understanding Gradle video on that topic. Now, with the enriched information, Gradle can automatically select a native jar file. If I just run the application as I do here in the example, it will select the jar file fitting the operating system I am currently on, which is macOS. But I could also tell Gradle to package my application for multiple target platforms if I want to create multiple deliveries for different operating systems. With Gradle's so-called variant-aware dependency management system and the ability to have arbitrary many tasks in a Gradle setup, I could even build all these distributions in one Gradle built invocation. As Gradle can then calculate different class passes or different module passes for different tasks that package different variants of my software. Another common case that we don't have in this example is that you want to modify, remove, or add a transitive dependency. This is also something you can do with the patch DSL. You mention the module where you want to change the dependency setup, and then you can remove or add things as needed. Before we look at the Maven setup, I just would like to mention that Gradle also offers alternative concepts and component metadata rules to influence the result of the dependency resolution. These other concepts were mostly added in early Gradle versions already before component metadata rules were added as a concept. Component metadata rules help me to more clearly think about what I need to change or need to patch, because they fit neatly into the model of thinking about modules providing sufficient metadata for the build tool to solve all the conflicts. That being said, if you know about other mechanisms and find them easier to use because you are more familiar with them already, you could use these as well, as long as you can isolate them into a separate file for dependency rules, as I have done here. The main point again is to not mix these into your build Gradle files where you declare the dependencies. In particular, if you want to use the Java module system setup, there's also no opportunity to do this, as the module info files won't allow you to formulate any patching of the modules you require. In the corresponding Maven setup, I've created a parent POM for the dependency rules topic. Maven unfortunately does not have a similar concept as component metadata rules in Gradle. Also, Maven does not support the notion of capabilities as Gradle does. Hence, we need to patch things more directly. Instead of enabling the build tool to detect the conflict and then making a selection if necessary, we directly remove things from the dependency graph so that the conflict does not even appear. So for a lot of cases, you can use the exclude concept in Maven. Here, you mention a module that brings in a certain transitive dependency and via exclude express that this dependency should no longer be added. The exclude concept can be used to solve a lot of cases, but can get hard to maintain in a large dependency graph. By the way, the exclude concept is also available in Gradle and can potentially be used as alternative to component metadata rules. The next case is the selection of native jars. Here it is important to note that there is a fundamental difference between how this is done in Gradle and Maven. Gradle has the so-called variant-aware dependency management and the concept of the task graph, which allows Gradle to build arbitrary many variants of a software in one go. Maven has a very strict lifecycle-based model when building the software, which essentially follows the idea that you build one variant of the software in one Maven call. Therefore, if you would build the software for different operating systems, you would call Maven multiple times. And then for each call, you would select a different so-called profile. The profile is a way to globally reconfigure a Maven build for a certain purpose. A profile can be activated manually via parameter when calling Maven, but for the case of building operating system specific software, it can also be automatically selected in a way similar to how Gradle automatically selected the right operating system for the machine I'm building on. So with the setup I've done here, Maven will select the jars that fit my operating system automatically. We saw that performing variant selection and dealing with incomplete or missing metadata works quite differently in both build tools. Gradle has added a lot of features in this area in recent years, which probably makes it a more suitable tool in larger projects. In particular, if you would like to base your dependency definition on the Java module system, Gradle offers the richer feature set to get to a clean and carefree setup. Still, for a standard Java project, a well-structured Maven setup can also be achieved. The point of the fourth item of the recipe is that if you need to add additional information because the build tool does not select the modules you want to have without it, then do that in a separate file and do not mix it with the dependency definitions in the build Gradle or POM XML files. And with that, if you follow these first 4 items of the recipe, you will get a well-structured and maintainable dependency and module management setup. Over time though, your dependency definitions, item 1, and the versions you select for third-party modules, item 2, will have to evolve with your software and with new releases of the third-party modules you use. How to deal with these 2 important aspects that concern maintainability over time will be covered in the next 2 episodes, starting with how to keep your dependency definitions in sync with the changes in your code. See you then.